Hello, I'm Adrien Rougny, postdoctoral researcher at ISMB, University of Luxembourg. Today I'm going to talk about a query-driven framework for constructing Boolean networks from disease maps and its application to Parkinson's disease. So what is a disease map? A disease map is a collection of diagrams that we call submaps, and each submap represents the molecular mechanisms driving a disease-related pathway. Submaps are highly detailed and they are manually created and annotated using standards of systems biology for their representation or their annotation. Pathways represented by submaps need to be studied together in a focused manner. For example, we might want to study a crosstalk that is upstream of a specific phenotype of interest. Diagrams by nature are static, so we need to build mathematical models to study the dynamics. And Boolean networks are a good candidate for this, since they do not require any dynamical parameters that are often difficult to obtain, and also because they are relatively scalable. So here we propose a new query-driven framework to integrate a disease map into a knowledge graph, select parts of interest from this knowledge graph, and then transform these parts into a Boolean network that can then be studied and analyzed. Our framework is divided in 5 steps. The input of our framework is a disease map, and the output is a Boolean network that models selected parts of this disease map. And at the core of our framework lies a Neo4j knowledge graph that allows us to integrate and transform the input disease map. So now I'm going to present the different steps of our framework. The first step is the extraction of the biological knowledge from the submap. So we extract this knowledge from and discard the diagramic part of the submaps. These models are instances of a well-defined hierarchical model encoded in Python. And this hierarchical model allows us to compare instance models and integrate them. In the second step, we do this integration. So we integrate our models into a Neo4j knowledge graph, and this integration allows us to easily query any element of the input models. In first step, we transform the integrated models into an inference graph in order to homogenize the types of relationship that are present in the graph, which eases the query of subgraphs. Then, in the fourth step, the user may query subgraphs of interest from this knowledge graph, and the user may do so using either relevant predefined queries and parameters or some arbitrary queries of their choosing. Finally, in the last step, we transform the obtained subgraph into a Boolean network. To do so, we use a generic transformation rule. And finally, the Boolean network that we obtain is encoded in an SBML qualitative model that can then be simulated and analyzed using state-of-the-art tools. So that is all for our framework, and we applied it to the Parkinson's disease map. In particular, we studied neuronal death in 2 particular submaps that are the inflammation and the neuron inflammation submaps. And we checked that the attractors landscape of the Boolean network that we built was consistent with expected behavior from the literature. To conclude, we built a framework to construct Boolean networks from selected parts of integrated disease maps. The integration of a disease map into a knowledge graph enables a full and easy access to its content and to its modeling using explicit rules. Future work includes defining different transformation rules depending on the context, as well as defining additional predefined queries and parameters. Finally, our long-term aim is to develop a fully programmatic, customizable, and reproducible construction of focused dynamical models from disease maps. Thank you very much for your attention.